Another test using the first derivative. This tells us how to find a local maximum or minimum. It doesn't say if you have a local maximum, then the derivative 0, like Fermat's theorem told us. So Fermat's theorem was what we discussed in the last section, and that was, you're already assuming you have a local extremum, and it's telling you that its derivative is 0. So the first derivative test is kind of going the other way. Suppose that you have a critical number for a continuous function f. If the derivative changes from positive to negative at that value, then f has a local maximum at c. So we saw that here. F prime changed from positive to negative at this local maximum. If f prime changes from negative to positive at c, then f has a local minimum. And actually, this is an example of that. So f changes from negative, here's f prime is this dashed straight line, to positive, and this parabola has a local minimum at the critical point, which is where the derivative is 0, which in this case is 0, 0. Here's another example of when you have a maximum. Here you see that the derivative is changing from positive to negative because the function's going from increasing to decreasing. And then there's the last case of the first derivative test, which is kind of inconclusive. If f prime is positive to the left and right of c, or negative to the left and right of c, then f has no local maximum or minimum at c. You know you don't have a maximum or minimum at that value, but so far it's not really telling you anything else about it. And we'll see that there is more information we can get from even this case. So here's an example of a function that has the derivative is 0 at when x is 0, but is negative to the left and right of that critical value. So it's not a max or min of the function f. So to an example of using the first derivative test, we want to find the local maximum of this function. Well, you find the critical values by first finding the first derivative and setting it equal to 0, and then testing around those critical values to see what the sign of the first derivative is there. So we'll test a value to the left of -1 and to the right of -1. And we see that the derivative is negative to the left of -1 and positive to the right of -1. So x equals -1 is a minimum. We see that from the graph. And likewise, we do the same with c equals 1. We test to the left of 1 and to the right of 1. We put those in the first derivative. The first derivative is positive to the left of 1 and negative to the right of 1. So I have a local maximum. One way to organize how to find the intervals on where the derivative's positive or negative is through a sign chart. So if you look at the derivative of this function, you can organize what the sign of that derivative on each interval around the zeros of the derivative, or the critical numbers, and then determine what f is doing on that interval. And then that helps you determine if you have a minimum or a maximum. So we just saw that the derivative was less than 0 to the left of -1 and greater than 0 to the right of -1. Therefore, the function is changing from decreasing to increasing at that critical value, and you have a minimum. And then you have the opposite case around value x equals 1, and you have a maximum. There's that third case with the first derivative test where it doesn't change direction on either side of the critical number. And so that's not telling you, so there's not a max or a min there, but it is telling you something relative to another characteristic of a function, and that's concavity. So for instance, if we look at this function, x minus sine x, on the interval minus pi to pi. If I take the derivative, set it equal to 0, I get the critical number at x equals 0. Now if I test on either side of x equals 0, if I plug minus pi over 2 into my derivative, I get 1. And if I plug positive pi over 2 into my derivative, I get 1. The derivative is positive on both sides of that critical number, so it's not a maximum or a minimum. But if you look at the graph of it, you can see that, again and again, these critical numbers that aren't max or mins are doing weird things with the graph. They're changing the concavity. So the concavity is the curvature of the graph. So at that value of x equals 0, the graph's not turning around, but it is changing from being curved down, sort of, at this to the left of the y-axis, and then it curves up. So at this point where the critical number is where it's changing concavity. Through these little bowls here, because another way of describing concavity is where the graph holds water. Is the graph curved such that it could hold water? So on this, to the left of the y-axis, where it's concave down, it's like a bowl upside down. It's not going to hold water. And here to the right of the y-axis, it would hold water. Sometimes concavity of a graph is very subtle, and it's hard to tell exactly if it's concave up or down just by looking at the graph. Here it's pretty obvious. Notice the tangent line. I've added the tangent line to the graph of this function. So it has a positive slope. It starts out positive. It would move for me. And then it's getting flatter. And it's horizontal at the origin itself. Then it starts increasing again as positive. So it never gets negative. It's always increasing. Another thing to notice, what this means is that when the graph is concave up, notice that the tangent lines, the graph is above the tangent line. And when the graph is concave down, the graph is below the tangent line. So that's the rigorous definition of concavity. Instead of drawing bowls, you have you look at the tangent line relative to the graph. So this, again, just kind of reiterates what was said before, that this is increasing everywhere, and that critical number is showing us where it's changing concavity.